Thermal expansion. All right, another way to think about temperature is that it's a measure of the average kinetic energy that atoms or molecules have. So every solid material, or all materials, are made up of atoms or chains of atoms, molecules. And due to their intrinsic kinetic energy, due to their temperature, they have this motion. They vibrate, they jiggle around. And the higher the temperature, the more they vibrate. And this means that when your atoms are arranged in some sort of grid or lattice, like they are in solid materials, an increase in temperature increases the amplitude of those vibrations, which means the atoms get spaced farther apart. Their average separation increases. That means the material gets bigger. That's known as thermal expansion. And thermal expansion is kind of a complex process and really depends on the type of material and the arrangement of atoms and so on. But we can come up with a very simple mathematical model for thermal expansion. And that model looks like this. The change in length of a material equals some constant alpha that depends on the material times the initial length times the change in temperature. Your textbook, by the way, has a typo. They wrote delta L over here. It's supposed to be delta T. Another way of writing this equation, the way I usually write it, is the final length of a material after it undergoes a temperature change equals its initial length plus alpha times initial length times this temperature difference. Those are just two ways of writing the same equation. And this thing alpha is called the coefficient of linear expansion. And it depends on the material. Some materials will expand more in response to a change in temperature than others will. So let's do a quick calculation. This is example 10.3 from your textbook. It has to do with a steel railroad track. And it says that we have a steel track of length 30 meters at 0 degrees C. And then, so that's maybe on a cold day, you measure this length of railroad track at 30 meters. And then on a hot day, it's 40 degrees C. We want to figure out how much that track expands. What's its final length? So a steel track, it's not really a sentence. Okay, let's say steel track has length of 30 meters at 0 degrees C. What is its length on a hot day when it's 40 degrees C? Well, all you got to do is plug into this equation. I don't have the numbers with me right here, but this value of alpha, I think for steel it might be 11 times 10 to the minus 6. I'm not positive about that. But your textbook has a table of values of alpha for all sorts of different materials. So get that data from your textbook, plug in the initial length and those two temperatures, and it should give you a value of 30.013 meters. Now, this is telling us that the railroad track just increased in length by 1.3 centimeters. So it got like this much longer. Now, that might not seem like a huge difference, but if you don't allow for any room for that track to expand, the only thing it can do is to buckle sideways. And there are some dramatic photos online, even in your textbook, of what happens when you don't allow a railroad track to have any room to expand. It buckles sideways and the track gets super wiggly, which will make a train derail. So what you do to compensate for the fact that the steel is going to expand with temperature is you put in thermal expansion joints. You put in little gaps periodically in the track, not so big that the train's wheels are going to fall off the track, but big enough that they can accommodate any sort of reasonable thermal expansion that might happen because of a change in temperature.